Today, we're going to crack the code on a pretty fundamental mystery of our world, the invisible science that keeps everything from a massive skyscraper to the chair you're literally sitting on right now from falling apart.
No, I mean, really stop and think about it for a second. What's actually keeping that huge bridge from just collapsing into the river? Or that skyscraper from toppling over in the wind? It kind of seems like magic, but it's not. It's physics. It's this perfect silent battle of forces happening all around us, all the time.
So let's break this down with something super simple, like this block. When something isn't moving, it's not speeding up, it's not spinning, we say it's in a state of equilibrium. It's just balanced. And that simple idea, that state of perfect balance, that is the goal for every single structure engineers have ever built.
So why is it balanced? Well, it's all because of forces you can't even see. The block's weight is pushing down, right? And the ground, it's pushing right back up with the exact same strength. They just cancel each other out perfectly. So to understand any structure, we first have to find a way to see these invisible forces.
So how do we see the invisible? Well, engineers have this secret weapon, a kind of special drawing that just cuts through all the clutter and lets us focus on exactly what's holding everything together. And it's called a free body diagram. You'll hear people call it an FBD. You see, its whole purpose is to take an object, what we call our body of interest, pull it away from everything around it, and then draw every single outside force that's acting on it. Honestly, it's probably the most important first step you can take to solve any problem in statics.
And making one follows this really clear 5-step recipe. First, you pick your object. Then, you basically imagine it just floating in space. You take away all its supports. Next, you draw on all the forces, gravity, and the forces from those supports you just mentally erased. Add in your measurements, and finally, you just label all the forces you don't know yet. Simple as that.
And this shows you just how powerful an FBD is. Look on the left. That's the real system, right? 2 blocks stacked. It's simple, sure, but there's still extra stuff there. Now look at the right. Wow, see that clarity? We've totally isolated block A. We can see its weight pulling down, the force from the side pushing on it, and the force from block B pushing up. It's clean, it's simple, and now we can actually analyze it.
Okay, so once we can see the forces, we need to know the rules they play by. And it turns out, for anything in equilibrium, there are 3 and only 3 unbreakable laws that have to be true. You can think of these as the grammar for this whole language of forces we're learning.
So rule number 1, all the forces going side to side in the horizontal direction have to add up to 0. Think about a game of tug-of-war. If that little flag in the middle of the rope isn't moving left to right, what does that mean? It means both teams are pulling with the exact same force, right? They're perfectly balanced. That's this rule.
Rule number 2 is, you guessed it, the exact same thing but for up and down forces. All the forces pushing up have to perfectly cancel out all the forces pulling down. This is why our block isn't suddenly flying up into the sky or sinking down into the ground.
And the third, final rule is all about rotation. Now, a moment, that's just the fancy engineering word for a force that tries to make something twist or spin. This rule says that all the clockwise twisting forces have to be perfectly balanced by all the counterclockwise twisting forces. It's exactly why a perfectly balanced seesaw just sits there, not tilting one way or the other.
All right, so we've got our drawing tool, the FBD, and our 3 rules. The very last piece of the puzzle is figuring out how real-world things, connections and supports, actually create these forces. We basically need a dictionary, something to translate a physical support into the forces we draw on our FBD. Okay, let's start with this one, the roller support. The best way to think about this is like a skateboard on the floor. It can roll back and forth, side to side, no problem. But you can't push it through the floor, right? So because it only stops motion in one direction, up and down, it can only create one reaction force, just a single push straight up away from the surface. You can see it there with that single arrow.
Next up, let's find the hinge support. Think about a regular door hinge. The door can swing open and closed, it can rotate, totally free. But you can't just pull the door up or down, or left and right off the frame. So, since it stops motion in 2 directions, it creates 2 reaction forces to do that job, one horizontal and one vertical. And finally, the big one, the fixed support. This is the strongest of them all. Picture a flagpole that's been cemented deep into the ground. It can't move up or down, it can't move side to side, and you can't make it tilt or rotate either. It's locked in place. And because it stops all 3 types of movement, it creates 3 reactions: a vertical force, a horizontal force, and a rotational force, a moment.
Okay, so now we have everything. We have the free body diagram to see the forces, we have the 3 unbreakable rules of equilibrium to do the math, and we have our dictionary of supports to translate the real world. We have all the tools. Let's go solve a puzzle.
Here's our puzzle, a simple beam. You can see it has a hinged support over at A and a roller support at B. And there are some forces we already know pushing down on it. Our mission, should we choose to accept it, is to figure out the exact strength of those unknown forces at A and B that are holding this whole thing in perfect balance.
Step 1. Always, step 1, draw the free body diagram. We take the beam, imagine it floating, we draw on the forces we know, and then we swap out the supports for the forces they create. So, the hinge at A, that gives us a horizontal and a vertical force. The roller at B, that just gives us that one single vertical force.
Now for step 2, we apply our rules. And listen, here's a fantastic pro tip. Whenever you can, start by summing the moments at a point that has the most unknown forces, like our hinge at point A. Now, why would we do that? Well, think about it. The forces acting at that point can't create any rotation around that same point. So they just drop out of the equation. It makes the math so much simpler to solve. And when we write out that moment equation and we do the math, bam, we find our first unknown. The upward force over at support B has to be exactly 7.216 kilonewtons. That's the only number that will keep this beam from spinning. The first part of the code is officially cracked.
And here's the cool part. Once you find one unknown, the rest just fall like dominoes. We just apply our other 2 rules. We sum the forces in the x direction. That gives us the horizontal force at A. We sum the forces in the y direction, and that gives us the vertical force at A. It's just that systematic.
And just like that, we're done. The puzzle is solved. Every single one of those invisible forces that's holding that beam perfectly still, it's not a mystery anymore. It's a number we know. We've taken this real thing and we've completely 100% understood the physics that keep it standing.
And you know what's so amazing about this? The 3 simple rules we just used for this little beam, they are the exact same 3 rules an engineer uses to design a skyscraper that's 1,000 feet tall. The problems get way more complex, the numbers get way bigger, but the fundamental code, it never changes. So the next time you're walking around, look at a bridge or a building or even just a street sign. Try to see past the steel and concrete. Try to visualize those invisible forces, that perfect, silent balance that's holding it all together. After this, what are you going to see differently?